here today. If you came in late, there are 4 sheets on the table back there. Go and get one of those. See how far we get today. First section we're going to talk about are rates of change in tangent lines to curves. What are rates of change? What are they? What do they define? How do we use them? Yeah. The acceleration is one of them. Is there another one? Yeah, just put a negative in front of it. You're right. Well, how many of y'all have taken a physics course before? If you haven't, then that's a perfect course to take after you learn calculus. Because physics is math in motion. Anything that moves, anything that grows or shrinks is defined by numbers. And that's what mathematics is all about. And physics is the application aspect of mathematics. So yeah, rates of change are slopes. We have 2 primary types, which are average and instantaneous rates of change. What's the difference? What do you think the average rate of change is? What does average mean? How do you calculate the average? Right, so it's a fraction of some sort. What formula do we use in algebra to find the average rate of change of a curve, of a line? Again, it's a slope. Average rate of change is a slope. So an average is you have to have 2 pieces of information and compare them. What is instantaneous? What do you think instantaneous sounds like? It occurs at one moment in time. Instantaneous. What is the rate of change? What is the velocity or the acceleration at that one moment in time? Well, let me get one of those sheets also so we see what. But, okay, rock falling is just gravity acting on it. But what about launching if you're going against the force of gravity? Why is the rate of change important to know there? Why is the speed important to know? Yep, it has to overcome gravity. The higher it goes, the less oxygen there is for the engines to work. So it doesn't have as much power. But the higher it goes, the more energy it uses, the lighter it gets, so the faster it can go. See, all these things that are working at the same time, so you can space travel. But in order to escape the Earth's gravity to go into orbit, how fast does it have to go? Not so fast. We have to reach at least 17,500. But yeah, the faster the better. Once you pop out, then you can just take it easy. But the magic number is 17.5. If you don't reach it, you'll never escape the gravity of Earth. You'll sink back down. You'll burn up in the atmosphere. So knowing how fast it's going. So how do we determine this in a moving object? How do you determine the average rate of change in a moving object? let's say a car or somebody walking or somebody running, how do you determine their average rate of change or their speed? What's that? I'm sorry? Distance over time, yes. We have a distance. This is x1, x2 over some change in time. How many of y'all are familiar with that symbol there? The delta symbol. This means change. In math, it could be x2 minus x1 or y2 minus y1. So the way it's read, this is a delta. Delta y over delta t. Change of vertical movement versus change of time. Okay, so that's what we're going to look at. Let's look at the first example in your sheets. A rock breaks loose from the top of a tall cliff. What is its average speed during the first 2 seconds of fall? If you haven't taken your sheets over there when you come in, they're back there in the back table. During the first 1 second interval between time 1 and time 2, what is the average speed? So we're looking for two things. Average speed during first 2 seconds. And then between time 1 equals 1 and time 2 equals 2 seconds. So how do we do this? How do we figure that out? Remember, we have a tall cliff. A rock drops. What is its vertical movement? What force acts upon a falling object? Gravity. What is the force of gravity? What is the speed of gravity? If you deal with metrics, it's 9.8 meters per second. That's metric. If you deal with the SAE, which is American, you use 16 feet per second. Now, those of you who go in the scientific field or engineering field, here you have a big problem. For example, if you are in a project of building a ship is not built in one location, like a cruise liner. It's built in like 7, 8, or 9 different countries, and the pieces are floated together and they're assembled. You see the problem with that? Americans are the only ones that don't do metric. Problem, if they build things and they don't convert it to the metrics, then their size of their part of the ship is not going to fit everybody else. So you have to make sure to begin with, you have to know what system are you using. So gravity in metric system is 9.8, SAE is 16. All right, so what formula are we going to use to figure out our speed? Average speed. What formula are we going to use? But since we're dealing with time, the function at time 2 minus the function at time 1 over time 1 minus time 2, or time 2 minus time 1. So what is our function? What is our function? It's either going to be 9.8 t squared or 16 t squared, depending on which one you're going to use. Let's go ahead and use SAE, 16. So our function is going to be 16 t2 squared minus 16 t1 squared, t2 minus t1. So we're going to use our speed, average speed. So in question A, what are T1, what are T2? Unless you know this stuff, then you have to be here. Don't take your phone out. What are the times? Yeah, T1, when it first starts, the time is 0. That's when it first stopped. And then want to know what it is at T2, which is after 2 seconds. So our speed, our average speed is 16 2 squared minus 16 0 squared over 2 minus 0. So that's what the average speed for the first 2 seconds of fall. B is asking up here, time is 0. But then it wants to know at time 1 and times 2. So do we use the same formula? Yeah, because it's looking for the average speed. Sixteen T2 squared minus 16 T1 squared, T2 minus T1. 2 squared minus 16 times 1 squared. 2 minus 1. Sixteen times 4 minus 16 times 1. 64 minus 16 over 1. .48 feet per second. Why is it faster for B than it is for 1? Why is B bigger than 1? Think of the rock. When it's at rest, how fast is it going? Yeah, as it starts at 0 and as it falls, it has to, does it go the speed of gravity instantaneously? No, it's got to pick up speed. So in that picking up speed, it takes time. So at each time interval, it increases speed until it gets to terminal velocity. In B, we already had the speed built up. From 0, from when it first started dropping to the first second, it started accelerating. Then when it got to time 1 and time 2, it's a little bit faster. Between time 2 and time 3, it'd be even faster. How fast can it go? No, what's the fastest it can go falling down? This is where physics come in. Did anything push it off the cliff? So it had no other force acting upon it. So the only force acting upon it is gravity. Can it go, because of that, can it go faster than gravity? Nope. So on a falling object, gravity is as fast as it can go. Galileo proved this a long time ago. He took he took a pound of feathers and a 1 pound rock and dropped them. Which one hit the ground first? Same time, because they're both a pound. He did this inside the Leaning Tower of Pisa. If you ever see the Pisa, it's leaning, yes. But inside there, it's a hollow cylinder. He did inside there because it would reduce the air effect on these objects, air resistance. So if you have the same amount of objects, same mass, the same weight, they're going to fall at the same rate. They're going to hit the ground exactly the same time. How about if you had a feather and a rock? Again, negligible, forget air resistance. If you have a feather and a rock, forgetting air resistance of the feather. They fall the same because remember, what's the only force acting on it? Gravity. So that's what he said. So now because of this, we could only reach our maximum of the velocity we can go is gravity itself. What's the difference then between speed and velocity? Because obviously we can, if gravity is 16 feet per second, we're going 48 feet per second. That's the speed. The velocity is going to be 16 feet per second squared. The difference is speed is change of distance over change of time. Velocity is a change of speed over change of time. Speed is distance over time. Velocity is speed over time. Acceleration is change of velocity over time. And we're going to look at those in depth, and we start doing the calculations part of this course. Question number 2 sounds like the same thing as the first one. So let's look at question number 3. Oh, that's average velocity, average speed. What do we mean when we say instantaneous rate of change or instantaneous speed? What do you think the difference is between this and the other one? What's that? Oh, no, we'll do example 2 in a second. But yeah, it has to do with a specific time. Because average speed, whether it's increasing or decreasing, that's increasing. The average speed of an object going up between 2 different time intervals. Instantaneous is only at one point, space and time. So how do we find the instantaneous rate of change? We know rate of change is the slope. How do you think we'd find the instantaneous rate of change? Well, the average. How is that going to work? What is the difference quotient? And how's that going to work? Remember, average rate of change looks at y1 to y2 between t1 and t2. That's the average rate of change. Rate of change. We want to know instantaneous. If you think about what's happening here, is both of these intervals are getting closer and closer and closer together. So now my T1 is here, my T2 is here, and then it gets closer and closer. What's happening here, as T1 goes to T2, Y1 is going to Y2. In other words, their distances away from each other are becoming close to 0. So what we have to do is we have to take these slopes of these 2 points and get them closer and closer and closer and closer to this T point right here. That's the difference. As the distances between T1 and T2 get smaller, so are these between Y1 and Y2. It's gonna get closer and closer and closer and closer to that. Eventually, as T1 becomes T2, at this point right here, at T, whenever T1 equals T2, then we have an instantaneous rate of change. And we'll have examples of that, which we have to just do that. We have to start with a wider range, find the slope between there, the average rate of change, and then make our intervals smaller and see where it's approaching. That's it. Let's go back and look at example 2. I just read what it said. Example 1 says, what is the average speed of this object? What we're looking for in example 2 is, what is the speed between that interval? A is looking for the average speed, which is the fraction we're looking at. And 2 is looking for the actual speed itself. So that's what the problem is, what we have to look at. So example 2. Speed of a falling rock at T1 and T2. So again, speed is the change of your position over the change of time. And that's what we're going to use. So we have 16 T1 squared minus 16, oops, T2, I'm sorry, and that's T1 squared. Let's look what this means now, because now what we have to do is we have to find the speed of an object, we cannot have two separate values. How are T1 and T2 related? T1, T2, Y1, Y2. What is the distance between T1 and T2? We define that as H. Or if you want to, you could also say delta T. But we'll use H because that's what we use for the difference quotient. So how do we use this information to define T2 as a function of T1? In other words, how do we get to T2 from T1? If H was 5, if T1 was 3, what would T2 be? Remember, H is the distance between these two. It's 5. It'd be 8. How do we get 8? No. We started off at T1. How do we get to T2? You add it, yeah. So T2 is equal to T1 plus H. So T2 is T1 plus H. And T2 minus T1 is H itself. So our first one, we're looking at T1, we're going to get when T equals 1. So when T1 equals 1. So we have 16, 1 plus H squared minus 16 times 1 squared over H. What do you have to do next? What is 1 plus H squared? 1 plus H squared is 1 plus H times 1 plus H, which gives us 1 plus 2H plus H squared.
Problems from previous stuff makes sense then.
Yeah, because basically we have to now combine all our terms we can. So we have to get rid of the parentheses. So this is 1 plus 2H plus H squared. 16 times 1 squared is 1. Distribute. We get 16 32H 16H squared minus 16 over H. Nope, H will be the last thing to get rid of. Let's get rid of the 16s first.
No.
Yeah, so now we have 32H plus 16H squared over H. We can factor out an H on top. Then what? Is that our speed? Well, do we know what H is? No, I mean, H could be, if we set it equal to 0, then we get our speed there. And remember, what does H represent? H represents the distance between the two times. So it all depends on what you define H as. Then that'll help you. That'll determine what the next one. So remember, what we're looking for is a speed at a certain time at 1 second. So what we're looking at here is we want our H to go to 0, so we get 32 feet per second. And we do the same thing for the second one for T equals 2. We put a 2 right there and 2 right there. No, let's go ahead and we'll do that one. So
So then for T1, you said it's 13 feet per second.
right. So T at 2 seconds. So our speed is 16 T1 plus H squared minus 16 T1 over H. 16. Now we're looking at 2. Sixteen, 2 plus 4h plus h squared minus 16 times 4. That's not true, it's 4. And that should be 4h and h squared. 16 times 4 is 64. Sixty-fours cancel. Factor out the h. Sixty-four plus 16h. When h goes to 0, we get 64 feet per second. So you see, what kind of math are we doing so far? Algebra. And we're going to be doing this a lot. Calculus is going to be nothing more than the first step. The rest of it is going to be this stuff. So you have to make sure you know your algebra skills. So that's the average rate of change. Any questions so far? So you have to be very careful whether you use 16 or 32 or 9.8 or 16.
Well, the question's either how to figure out what H is, or are we just gonna use H for whatever we want?
No, H will usually always go to 0. Good question. Very good question, actually. This next section, we're going to talk about the average rate of change and secant lines. We just looked at average rate of change and tangent lines. What's the difference between a tangent and a secant line? I hear crickets. What's the difference between a tangent and a secant line? No, stop. I don't want to hear. If you have to read, don't answer. If you have to read, don't answer. I can do that myself. I want to know what you know. So if you're going to read, don't answer my questions. How many of y'all took trigonometry and pre-calculus not too long ago? This is where you should have known that stuff first. A secant line, by definition, crosses a curve at 2 points. And that's what we just did. Our first examples, we did actually find the slope of 2 points. And then we use those 2 points to find the slope of a tangent line. A tangent line touches a curve at one and only 1 point. That's the difference, which is the difference between algebra and calculus. Algebra cannot find the slope of a single point. You're not taught in that class. Because what is the slope defined as? The 2 points. You need a y1, y2, x1, x2. So the average rate of change by definition, I think I put that, can I give you that sheet? Average rate of change of a function, y equals our function f of x. On a closed interval is defined as the vertical change over the horizontal change, which is y2 minus y1, x2 minus x1. And these functions and that's from algebra. And h is the distance between x2 and x1. So it defines x2 as being h plus x1. So we have x1 plus h minus f of x1 over h. That's your average rate of change. Yeah, you have to make sure that your denominator is not equal to 0. That will be taken care of later on. Does that formula look familiar to anybody? Does this formula look familiar to anybody? What is it called? It's called a difference quotient, right? The difference quotient, by definition, finds the slope of a curve, the slope of a function between 2 points. And we could make those 2 points closer, closer, closer by making h get smaller and smaller, 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 smaller. Do we have 3 yet? No. Let's look at example 3. Find the slope of the tangent line to the parabola y equals x squared at the point 2, 4 by analyzing the slope of the secant line through 2, 4. And write the tangent line to the parabola at that point. Basically, what they're saying for example, if we had a curve, we had a point. The slope of that point, of the curve at that point, is defined by this tangent line. The slope of the curve at a point is equal to the slope of the line tangent to the curve at that point. Let that sink in. the slope of the line tangent to a curve is equal to the slope of the line tangent at that point. So in other words, this line and this curve both have one thing in common: the rate of change at that one point. Mathematically, historically, that was a big step. Because who would ever think that a line and a curve can have anything in common? But when you put them both together where they touch, then they have the same rate of change at that point, which is pretty interesting. All right, so example 3. Find the slope of the tangent line to the parabola y equals x squared at the point 2, 4 by analyzing the slope of the secant line through 2, 4. Then write an equation for the tangent line at that point. So we know that our slope of the tangent line is given by this formula. Let's go ahead and fill that out. So that's going to be f of x1 plus h minus f of x1 over h. So what is our x1? Two. Very good. That's our point we're looking at. So what we have here is 2 plus h squared minus 2 squared over h. Why is it 2 plus h squared? Because our function is x squared. Our function f of x is x squared. We have to FOIL the first one, so we get 4 plus 4h plus h squared minus 4 over h. The 4's cancel, so we have 4 plus or 4h plus h squared over h. Factor out the h. So what does that represent for us? What does 4 plus h represent? Look at your notes. What does that formula define for us? Nope, it's a slope. It's the slope of the secant line. We just defined it a second ago. So now what do we do from there? So as h goes to 0, our slope becomes what? So as h goes to 0, our slope becomes 4. What does that have to do with the whole thing? What does this have to do with the whole picture we're doing? Remember, we took h to be going to 0. This was the slope of the secant line. As h goes to 0, what does this become now? This is the secant line, right? That second one. The slope of that one was 4 plus h. What does h represent? The distance, the horizontal distance between these 2 points. That's h. When h goes to 0, what happens to this secant line? Well, these points get closer and closer together. Eventually, they become this when h goes to 0. So the slope of the secant line is 4 plus h. The slope of the tangent line at that point is 4. Right, so what are we looking for here? Find the slope of the tangent line of the parabola, analyzing the slope. Yep. So we have the slope of the tangent line. Write the equation of the tangent line to the parabola at that point. So now we have to find the equation of the tangent line. At the point 2, 4. So how do we figure that out? So again, our slope is 4. We're looking for the equation of the tangent line. So what equation, what's the equation going to look like? What's the form of an equation of a line? Right. So what do we know from here? We know our slope is 4. Now we have to fill in the rest of that blank. It has to be the line tangent to the curve. What's the curve equation? X squared has to be tangent to it. So what's our equation and what's our y-intercept going to be? Because our x value is 2, it's shifted. That means it's shifted 2 to the right. when X is 2, that goes to 0. And so that means this makes it our y-intercept. Because we're using the 0.24. So now we'll get rid of the parentheses. So we have 4x minus 8 plus 4. Y equals 4x minus 4. This is the equation of the line tangent to the curve at that 0.24. So think about what we just did there. We have to first find the slope. How do we find the slope of the secant line? The y2, with the difference quotient. That gave us a slope. Once we know that, we have to figure out what is from our x value, what is our horizontal shift for our new curve? We shifted up 2 to the right. And if we plug in our 2 inside there, our y-intercept is going to be 4. And there's our example. Let's look at the next part. Rates of change and tangent lines. I don't want that. Oh, that's when we need these next pictures. Now, the rates of change of tangent lines we're looking at here now is the rate of change of, it's called instantaneous rate of change. So if you look at our picture of example 4, we can find the average rate of change between any 2 points. For example, between this point and this point. So between point P and Q, find the average rate of change. What's it going to be? Example 4. So we have point P is at 23,150. Point Q is at 45,340. The average rate of change between those 2 points is what? So it's going to be the change of our points over the change of our time. So it's going to be y2 minus y1 time 2 minus time 1. This is point 1. This is point 2. So the y values. The second y value is 340. The first y value is 150. 45 over 23. 190 over 22. So that's, and what's that going to be in decimals? So in this, these are the number of flies over 50 days. So these are 8.6 flies per day. That's the average rate of change of flies, since it's increasing. So the average is pretty straightforward. That's stuff we've been doing all along. Now, how do we find the instantaneous? What the instantaneous part will look like let's say, because this is at, let's, to find the instantaneous rate of change, what we need to do is find the slope of that tangent line there. How do we find it? We take 2 points and find the average rate of change there. Then we move them closer. Then we move them closer. Then we move them closer. So in order to find the instantaneous rate of change, we have to look at a pattern going. Because we won't be able to just find it at that 1 point space in there. We have to take these secant lines and get closer, closer, and closer, and closer, and closer until we find the actual rate of change. So let's go ahead and do that. Looking at our picture, oh no, so the first example 4 is just looking for the average rate of change between 23 and 45. Example 5 is looking for instantaneous. What is happening exactly on day 23? So example 4 is the delta P over delta T. That's what we just did. That was the 8.6 flies per day. Now, for this example 5, we have to first pick 2 points that are not on 23. You pick 2 points, let's say that one and that one. Find the slope of that one. Then let's get closer. We'll get this point and this point, and that'll be closer. That's it's gonna be time consuming. I'm not gonna lie to you. So what was the first pair of points you used? I mean, we could pick points like that, or we can use that as one of our points. And eventually that will get us closer and closer, closer. So let's call point 123, 150. And then point 2, we can use, well, we used 45, 340. Point 2, the next one we can use would be 40, 330. $35, 310. So all I'm doing is just looking at this. I'm gonna start from this one. I got that one, that one, that one. Because we're going to 23, so I have a couple more to look at. That one's gonna be approximately 27 or 270. And then at 25. So I'm just gonna leave, I'm gonna fix point 1 at the point we're looking at. And if you notice what's happening in each of these points that I'm picking, the graph, the slope of the curve, that line is getting more and more steep. Eventually, the closer I get to this point, the more accurate my approximation will be. So let's do those. So here's that 45, 340. The slope is going to be, remember, I'm using 23, 150. So it's going to be 340 minus 150, 45 minus 23. And we just did that. Yeah, so it's 190 over 22. Then the second one will be 330 and 40. $17. $180. What's that one gonna be? What's that? 7.5? And then the next one I used was 310.35. So it's 310 minus 150 over 35 over 23. This was what?
That's great. The last one was 10.
Which one? Last one? This one?
I mean,
Was 10.5? Right. Then 270 and 30. $270 over 110. 30 minus 23. 120 over 7. $170 and 25. $20 over 2. Oh, that's not right. It should be getting larger. Anybody cross-referencing these, if they're correct? Because if you notice, it's getting steeper and steeper and steeper. So at 25. On this last one?
That 160.
Yeah, just do, the 120 over 7. And then 20 over 2, it's pretty straightforward. Unless that's not 170. Unless that's 190. And that make it 20, which makes it more like it. So as we can see, the closer we get to our equation, it's gonna be around 20, 21, 22. That'll be the slope around that point.
You said 190.
Yeah. 190 minus 150 is 40, over 2 is 20. But that's pretty much how that works. Instantaneous rate of change, you have to approach your point in question slowly and then see where your value is going. All right, so that's that section. Let's look at limits. Because that's what, in essence, that's what we've been talking about.